So today we'll take a look at this topic of voltage scaling. Voltage is a very powerful knob you have to reduce power consumption and make things more energy efficient. So if we go back and recall the equation which we looked, which governs the which basically tells you what is the power dissipation in the CMOS circuit, we basically had two terms: the dynamic power term, which is essentially CV square F for each node, and the static term, which is independent of the activity of the chip. As soon as you connect it to the power supply, you have leakage current, and so there is a leakage current for every gate times the power supply voltage. That is the leakage power consumption. And if you see here in the last class, we looked at ways by which you can reduce both of these terms, look at switching activity, look at sizing to reduce capacitance, look at how you can reduce leakage by using multiple thresholds, do power gating, look at input vectors, and so on. So today we'll look at this variable VDD, which allows you another very powerful way to reduce the power consumption and make things more energy efficient, both power and energy. So if you recall the delay for a CMOS logic gate driving an output capacitance. Capacitance is its self capacitance wire plus the load capacitance. So there is a average current, you can say, which the gate provides to either charge or discharge, and that average current you can kind of say is related to the saturation current, VDD minus VTH. When the transistor is in saturation, there is an overdrive, and then there is a factor alpha. This alpha is not the same as activity factor. This is basically, it's for 1 to 2. It's a number between 1 to 2, and really there is a capacitance C which you discharge. So there is CVDD. The charge is CVDD, and then you discharge through this current I. So the delay is charge by current. That is the equation for delay. Now, so that's why, inspired by that, we have this equation. Now the thing is, the delay of a combinational, or delay of a chip is essentially the max of the delay of all the paths. So you look at the critical path, which is a sequence of gates. So number of capacitors are charging and discharging and so on. So that is why we just say the delay has this functional form VDD by VDD minus VTH to the alpha with some proportionality constant K. K is determined by the actual logic circuit, the capacitances you use, etc., etc. But as far as the functional form goes for the delay of the chip, you can kind of say this is a good approximation for the delay of the gate. Now the frequency, so say you have a clock, so you have this delay of the worst path in your chip. Now you say I'm going to use my clock of the same period, so then the frequency of the clock is 1 by the delay, VDD minus VTH by KVDD. So now you can put that into the equation for the power. So what here we are saying is that you're running at a certain frequency, at a certain voltage, you're running it at the max possible frequency allowed by the chip based on the actual design and the critical path, and the power dissipation at that frequency is essentially can be written like this. Now I just want to kind of go into this equation a little bit so that you can see that it's not that difficult to derive this equation. First is what I've done is I've taken this leakage current I, and remember the leakage current has a functional dependence on the threshold voltage. Here we are looking mainly at subthreshold leakage current, not the junction and leakage currents. The subthreshold leakage current goes as e to the minus VTH by VT, right? And VTH itself has a dependence on the supply voltage through the Dibble effect, right? the off stack of any CMOS gate sees the full VDD across it, so it will modulate the threshold voltage. So VTH reduces by a factor. We call this eta times VDD. Eta is the Dibble coefficient. So so that shows up here. So I've just, and then everything else I've pushed it as constant K2. I just want to bring out the dependence on VDD. Okay. Similarly, out here in this again VT. Okay, so I made a mistake here. This VTH is some VTH dash independent of supply minus eta times VDD. The Dibble coefficient eta times VDD. So that's what. So I've just taken that out, and now I have 1 plus eta VDD comes here, and then this should be VTH dash. I should have put that some dash, but there's a typo. I'll fix it in the slides. So now you have an equation for the power as a function of the supply voltage, where you're running the, for every supply voltage you're running the chip at the maximum possible speed given by this. Now how does this look? How does power versus VDD look? So this graph sketches it. You can actually go back, for example, you can get these parameters K1, K2 and fit it, and you can, for any circuit, and you can plot this equation. So I'm kind of just sketching it out here. So kind of ignore these wiggles out here because I did this through PowerPoint, so it's difficult to draw a smooth line without wiggles. So it's just some kind of a smooth curve like this, and what we are plotting on the y-axis is the power as a function of, okay, I should have said versus VDD, versus function of supply voltage, not frequency. So it has some shape like this. Now if you look at the delay out here, there is a minimum voltage at which the circuit will work. We kind of discussed that in a couple of lectures ago. There is a minimum voltage, and theoretically the minimum voltage is pretty small, right? We said it's 2 times thermal voltage times log of 1 plus n. That turns out to be about 48, 50 millivolts or something, and people are able to also work down to, in silicon in laboratory they can go down to about 100 millivolts, and people report chips in literature 180 millivolts and so on. So 200 millivolts, if nothing else, is kind of reasonably is reasonable to kind of expect this voltage to be. Okay, so now of course at this regime out here between 200 to 300 millivolts or 350 millivolts, you are in the sub-threshold regime. So you have to be careful. I mean, you can't use this equation for delay, because this delay assumes a super threshold operation. So here you have to replace this current I by the sub-threshold equation for the current. Okay, so when you plot these kinds of curves, you have to make sure you use the right equations. And of course, there is a certain maximum voltage which you can use for your chip. That maximum voltage is governed, is basically determined by what voltage will break down the transistor. The transistor has very small geometries, right? The oxide thickness is very small and so on. So the electric field is basically the voltage divided by the distance. That is the electric field. So when you have very large electric fields, it can pull out charges and essentially damage the device. So that determines VDD max, which is usually about a volt, 1.2 volts is what it is right now in the modern processes. So you have the delay which grows, and here it just goes exponentially up because the current reduces exponentially. So the delay just goes up exponentially, and then you have power out here which goes like this. So there can be a dramatic reduction in power by reducing the supply voltage. Okay, an order of magnitude reduction in power. Easily, you can get easily by reducing the supply voltage to reasonable values. So now to kind of capture, you have say multiple different designs, and someone might have a watt of power but running at 100 megahertz, and someone else might have half a watt running at 80 megahertz. How do you compare the two? You can't just look at the power by itself because the frequencies are different, right? So how do you compare designs which have different frequencies and of course perhaps different power? If they had different frequencies and the same power, which one will be better, right? So you can kind of say, out here my delay is fixed, that is frequency is fixed, and one guy has lower power than the other, then. But if the delay and power both are different, how do you compare designs? Which is a better design? So one possibility is what is called a power delay product. You just take the power consumption multiplied with the delay. Okay. Now delay could be the frequency of the period of the clock cycle at which it's running. So when you do that, so especially if you have something like a microprocessor. Okay, this I made a mistake here. So this power delay product, if you want a better design, it should be the value of PDP should be low. Either what that means is either for the same delay I have lower power, or for the same power I have lower delay, that means higher performance. So that is good. Equivalent to this for microprocessors. When you have microprocessors, there is the performance, or instead of delay, you have the measurement of operations per second or instructions per second. So that is millions of instructions per second is MIPS. So you can look at MIPS per watt, because MIPS is millions of instructions per second. Second is down, watt is also down. It's 1 by power delay product. So for that, higher is better. Higher MIPS per watt is better because it's inverse of the power delay product. So there is a typo here. It should have been higher is better for MIPS per watt, lower is better for PDP. They are just inverse of each other. You can have, suppose it's not a processor, it's some cryptographic engine, then you can think of number of operations per second, number of encryptions per second. You can, whatever is the application done by that particular piece of logic, you can look at the rate at which it's doing that, look at the power consumption, and then come up with this number, this metric, and then you can compare different designs. Of course, when you look at this power times delay, that is basically energy. So what you are saying is something which consumes less energy per operation. Okay, this is energy per operation because you have taken power consumption and multiplied with essentially the period. It's like the energy per operation. You can say maybe the average energy per operation, because different operations might take different amounts of power, but you measure the power in the lab, you turn it on, let it run something. Over a period of time, you measure the power, you get a notion of average power, right? Then you say that is my power consumption, averaged over a number of different operations, and then this is the frequency, and so power delay product is essentially the energy per operation. Now the thing is, what this is saying is that lower energy per operation is better. So you take two designs, one design, and you say the design which has lower PDP is better than another design which has higher PDP, which translates to the design which has lower energy per operation is better than another design which is higher energy per operation. Okay. Now the problem with this is that this metric, I mean it's okay, nothing wrong with that. It doesn't capture the performance here. Okay, because you can get very low energy per operation if you run very slowly. When you look at the sub-threshold regime of operation, it turns out that the power delay product here will become very low. The energy per operation becomes very low when you go to the sub-threshold region of operation. There the speeds will be very slow, kilohertz. So, if you are just being graded or whatever evaluated based on energy per operation, you'll just go and push it into the sub-threshold region of operation. Of course, things will be very slow and it might not be interesting to anyone, right? So you want to kind of balance, this power delay product by itself doesn't give the whole story in some sense. So you want a better balance. So what is done is the metric is an energy delay product, where you take also EDP. EDP is energy per operation times the delay per operation, which is the clock period. which also is power times delay, because power times delay is energy, which if I were to go back and think of a microprocessor is MIPS square per watt, because delay comes 2 times, so MIPS is instructions per second comes 2 times. I mean the inverse of MIPS square per watt, right, is the power delay square. This also happens to be this concept of action in physics, and there is this principle of least action which is used to argue sometimes as to why certain things happen the way they do, because they take the least, is the path of least action, which probably a lot of the grad students are familiar with. Path of least action to get the job done. So it's not an unfamiliar concept. So, but this is basically, it has a nice, shall we say, it has a nice significance, energy delay product, which you would like to minimize. I mean, if you have 2 designs and you want to see which one is better, you look at the energy delay product and you say the one with the lower EDP is a better design than the one with the higher EDP. Of course, you can change the weightings. You can say, look, I really am more interested in delay. So then you might come up with a metric ED square, not E times D, but E times D times D, or E times D times D times D, and so on. So it depends on how what you emphasize. So people also have energy delay square and so on. So, but in the absence of anything, if you are just looking at ways to compare designs and the efficiency of designs, you would use the energy delay product as a way to compare designs. So let's go back to our equation again. I mean, it looks kind of complicated, but really all I'm doing is I took the equation for power. Remember, I had this, I just removed the frequency term. I then made it as a function of supply voltage. And then what I did was I also multiplied with the delay term. Delay has VDD by VDD minus VTH to alpha. So I just multiplied that. And then you can multiply it again by delay again to get the EDP. You get this equation, EDP as a function of VDD and threshold voltage and so on. So these kind of analytical formulae are kind of very useful. Of course, there is a certain model, simplifying model you use, and then there are certain constants like K1, K1 dash, etc., which you fit. You take the actual circuit, you kind of do a few simulations, and you get these parameters, and then you fit it, and you get this characterization of your circuit, which then you can use to figure out what is the right setting for some of these parameters. The analytical formula allows you to get to your answer quickly, and there is a certain, method or certain insight you can get. Of course, you can do a brute force search. VDD, suppose you want to find what is the best VDD, you can set it up, just do a brute force search for different VDD values and measure and so on. But this allows you to kind of get close to the answer, and then around that answer, if you want to do further optimization, you can kind of play around and get the values. So, in the quest of scaling VDD, what is the right VDD to use, right? So that's where we are kind of going towards with all these discussions. So when you can look at as you said, you have energy and delay, right? Nothing is free. You try to reduce one, other increases. So there is a trade-off. That is why we said we have the energy delay product, right, which you try to minimize. So when you look at at a particular choice of designs, a choice of implementations for a particular design. So here what you have is on the y-axis I'm plotting the energy, and on the x-axis I'm plotting the performance. So you have various choices, right? As a designer, you have choices at all levels of the design hierarchy. Architecture, microarchitecture, what is microarchitecture? Architecture maybe, what kind of memory I'm using, caches, etc. Microarchitecture could be how many pipeline stages, how many things running in parallel, do I have a hardware engine. So sizing is another. As a designer, you have a choice for sizing, what kind of sizes do I use. And now we are also talking about voltage is a choice for you. Threshold voltage could be another. So you have so many design parameters. And all these design variables, as a designer, you can can vary, and every possible value you get a particular design which has a certain energy, certain performance. Some of these parameters are discrete parameters, like choices for architecture. You can't there are discrete choices, either do this or do this or do this. Do I use distributed arithmetic or do I use multiply accumulate? These are discrete choices. But then you also have continuous choices, that is voltage. What voltage should I use? Right? So no matter what, you have a family of designs. Okay. So this exploring this space of designs is called design space exploration, and sometimes you have support for tools to do it, sometimes you have to do it yourself. For example, if you have you decide on a particular architecture and a microarchitecture, and you find out the critical path, then you can model the critical path's delay as a function of supply voltage, and then that restricted for that kind of design, if I were to find what is the right voltage. So now that you can, the previous equation we saw, we can model the energy versus voltage, frequency versus voltage, and you can kind of explore that in an analytical way. Otherwise, you have to have ways by which you try out these different things, and you get for each one you get energy versus performance. Now when you do that, you get this family of designs, and then you get this what is called the frontier, right? You cannot get anything on this side, below that. You get everything out here, and then you have something out here at the boundary. In some sense, the designs at the boundary are the best. Anything out here, right? For example, if I have a design out here, then you could do something to get improved energy for the same performance, or improved performance for the same energy. Either you can come down vertically, or you can go horizontally to the right till you hit this frontier. This frontier is called the Pareto optimal frontier, where now it's not free. I cannot, if I try to improve energy, I'll reduce performance, right? I cannot go beyond it. I cannot come down like this, right? If I want to reduce energy, I have to lose performance.
So, but why is that? How do we have this curve? Why can't the other region where there'll be high frequency at a lower energy? Why isn't that region a feasible region?
All these are feasible regions. So you have, naturally what happens is that, so this is just a cartoonish representation. Okay, the exact curves will really depend on your particular function you're trying to implement. But in general, higher performance will be higher energy. Okay, now having something out here on this side where you have high performance and very low energy, okay, it's going to be, it's going to be almost impossible just from a physical perspective. Okay, so in general, if you want to push speed, you'll have to pay the price in energy. So that's why you have this thing which is going like this.
Sir,
Yeah.
what is the boundary of y-axis where it is closing?
Here, okay. See, one of the things here, if I intentionally did it like this to show that even when frequency is 0, you have energy consumption because of leakage. Okay, so that's why I just kind of wanted to point this out. So, so this is what is called the Pareto optimum frontier. So ideally, as engineers, as when you're doing design, you want to be at that frontier because no one can beat you. If someone says that they have better performance, then they are paying higher energy, and vice versa. Whereas if you are somewhere inside, then there is a possibility that someone can beat you in terms of doing a better design, which either reduces performance or increases performance at the same energy, or reduces energy for the same performance.
So most of the parameters which you are giving it closer to the performance.
Right. So these are basically all the things we have been looking at so far, all the different techniques and so on. They all go towards getting you down to the optimal point. As I said, some of these things are discrete things you have to try out. There is no mathematical formula which will tell you, okay, do distributed arithmetic versus this. I mean, these are discrete choices, right? Whereas something like energy versus voltage, we could have some formula which will allow you to do. So it's a combination of all these things which will, which describes the design space. Okay, and then it might be the case that there is some designer who has a completely wild way of doing it, and we haven't thought of, and that could change the whole thing. Where you have very high performance but very low energy. Maybe you're just doing something completely differently. So it's kind of a conceptual, but in general it will look like this. It's a conceptual way of looking at it, where you have a number of feasible designs, and then you have this frontier where you can do the best. Now remember, we are not saying which point in the frontier is the best. All these points on the frontier has a certain notion of optimality, because for that particular point, if you try to improve energy, you will degrade performance. Okay, where should you sit? I don't know. If you are sitting here versus someone else sitting here, I mean, both of you are at the frontier. Okay.
So, here it says constant one or based on parameters the frontier can change.
Frontier has a notion of something independent of the parameters, right? I mean, it's the best you can do. Sometimes you may not be able to articulate it. See, this is a conceptual thing. Can you really figure out, are you at the frontier or not? Right? It might be difficult. For example, if you are
asking, say, we are changing a material, then can the frontier be changed?
Absolutely, yes, absolutely. So that could be one of those, what shall we say, paradigm changing things which will push you, where you could get higher performance with lower energy, because you just totally change the material, right? Totally change the way, instead of doing classical computing, maybe you're going to quantum computing, right? So where you're working with spins, nuclear spins or whatever. So those are, I would say, paradigm changing things which will just change it. But no matter where you are, once, I mean, within that space also you will have this trade-off, energy versus frequency or performance, and there will be a notion of a frontier. You can say subject to certain things being constant, subject to a 130 nanometer process. Let's not even talk about quantum computing. Let's talk of 130 nanometer process versus 65 versus 45 versus etc. The frontier will be different for each other. Clearly for 45, as you scale down, it's better, right? That is why we are scaling down. So, but within that technology, you will have this. This is a conceptual framework. Now, what is the front? How do I figure out, am I at the frontier or not? So that becomes something where you kind of look at. Firstly, if you are in industry, you don't care too much about these things, right? You kind of want, because what you're given is a certain performance and you have to minimize it. Okay, the problem comes when, have you done the best you can? That's when the question is, like, or will your competitor do better than you? So then, just purely saying this, then if you know that you have done something where you are at the frontier, then you don't have to worry, right? No one can beat you, because you have done the best. If at all, they'll be at a different point in the frontier. Now, how do you know you are there or not? It can become a little difficult, and I don't think so. One way could be to maybe do local changes, and you see, are you able to improve without degrading one of them? Because one of the characteristics of being at this frontier is that if you will always have a trade-off, right? If there is a way by which you can improve without affecting performance, then you know that you have done better. Let us say what you do is non-critical paths you change to high threshold voltage. So you have reduced leakage and so energy reduces. But I have not changed performance because critical path has not been affected, only non-critical. So what you have done is you have come down. So that means clearly you are not at the Pareto optimum. So these are some of the things you'll have to basically do. You have to do a change and see if the change helps you to improve without degrading the other things. Now, within the frontier itself, if you are at the frontier, as I said, there are two people at the frontier. Who is better? Now, as I said, maybe at this point we bring in this notion of minimum energy delay point. Okay. So, in this energy versus performance, remember performance is, right now we'll say it's the same as frequency, the rate at which I'm doing operation, which is 1 by delay. So, energy times delay is same as energy divided by frequency, E by F, which is the slope of these lines to the origin. So when I want lower EDP, energy delay product, I want to have lower slope. So what I have to do is, if you are at some point in the frontier, you will pass a line from the origin through that point, and then you have a certain slope. Then you say, okay, if I want to do better, you have to take this line and turn it till it becomes tangential. Then this becomes a point of minimum energy delay product.
curve and hyperbolic energy into power is energy and frequency equal constant.
Energy by frequency is a constant, not energy into frequency. Energy by frequency. Remember, I am plotting on the x-axis frequency, which is 1 by delay. So energy by frequency is a constant. It's not a hyperbola. It is this curve, this straight line. Y equal to mx plus c, right? Y by x. That is what I am plotting. Energy by frequency.
Our actual graph.
This graph is not a hyperbola. No, it is. It has some shape. It will have this kind of a shape, because you try to push energy, you work very hard. Try to push performance. There is a max performance you can achieve. For example, minimum, equal logical effort gets you to a certain max performance as far as sizing goes. But there is a large energy cost. So as you try to push performance, it's natural to expect energy cost will go up very rapidly. That's why this curve has this kind of a shape. Right? It kind of like a hockey stick. It just goes up. So now suppose I had here what I am doing is, what we have now is this. You have a design which has, for a particular design, let us say a single core design, right? You have a energy delay, energy performance graph, and this is the frontier of the graph, right? Now I'm saying performance is basically throughput. So now what I do is I replicate it. I have two of them. You did one design, I put one more design. Both of them are running in parallel. Okay. So what happens is that you get a different energy performance curve. Of course, when you have two of them, you can get potentially more performance because there are two of them running in parallel. So that curve extends beyond this. See, you get a certain max performance with a single curve. With a single core, you could push whatever you could, but you want more performance, right? So I say I'm going to have two of them, and three of them, and four of them, and so on. So what happens is that the overall system, you see, I can think of this global kind of optimum, global Pareto optimum, where at some point, for example, if you come here, say you want more and more performance, right? I need more. So you start with a single core, you push, you get to a point at which it becomes better to actually switch to a parallel version. So instead of one core, now you start riding on this curve. And then beyond a certain point you go on this, and so on. So basically this is kind of the reason why people are going to multi-core, because to meet the ever increasing demand of throughput, there is only so much you can do by pushing the throughput of a single core. It just becomes, if you want a throughput which is out here, it just becomes very, very energy expensive to increase the clock speed, because clock speed will give you throughput, higher clock speed, higher throughput. As we said, critical path you want to reduce. Highest performance processors have 14, say fan out of 4, 12 to 14 FO4 delay. You want twice the throughput. So you say I'm going to go to 6 FO4 delay. So you see the number of flops you have, right? Every 7th gate, huge number of flops, huge power. At the extreme, you have just a sequence of flops. The flop has some embedded logic in it, right? So imagine that is the fastest you can do. A NAND gate with a flop. That will be a universal element in some sense. That will give you the highest performance frequency. If you could generate a clock which will drive that, but it will have enormous amount of power because the clock is going to every gate. Every gate is a flop. Okay, so it will just be off the charts here. So it's not sustainable. So instead of that, you say, okay, I'm going to go to a 2 core. Beyond a certain point, I'll go to 3 core and so on. And that is why you see now industry, you have multi-cores happening. 4 core, 16 core, 32 core. So that is the way basically things are evolving. Things will become very parallel. Okay, what I meant by core was I was using the terminology from the processors. A core is a processor core. But it can apply to any piece of logic. Say you are building an encryption engine and you want a certain throughput, certain encryptions per second you want to do. So you design it. Then tomorrow someone says, I need more. So what do? You have a choice. You can either increase the frequency of what you have by resizing, doing something, or you say I'm going to put 2 of them. So at some point, it will become more efficient energy wise to put 2 of them as opposed to just sticking with one and cranking up the speed, trying hard to crank up the speed. So that's what I mean. So it could apply to anything, any piece of logic which is doing some computation. You could look at beyond a certain point, you have to go parallel to get the throughput.
The core is completely of different material.
Not material, it's in the same chip, the same design you replicate. We'll kind of see that.
May not change.
Pardon?
You're changing the frontier.
Frontier is
Has got some like
exactly the second one. This is the frontier for a 2-core design. So for lower performance, a 2-core design is not that useful because you have additional hardware you have put. Okay, but for higher performance beyond a certain point, a 2-core is better than a 1-core. So the frontiers cross each other. That is where you have to go. So the global frontier should be hugging this. It should go. The global frontier will go like this. It will be hugging these frontiers. It's kind of the outer hull, if you can say, of all this, of all these feasible points.
if I have 100 cores and my weight of my speed too low, I can get equal performance of 10 core and to make
Correct. So we'll see that next. What are the drawbacks of going to multiple cores? We'll see that. So basically what we are saying is, again coming back to answering this question of core, it could be anything. For example, you have a piece of logic A. Really what we are saying is parallelism here. You want to use parallelism. Parallelism can occur in 2 ways. One is spatial parallelism, where 2 things are replicated in space, like AB is replicated again, and what you do is, instead of, I want a throughput of F, but what I do is I run 2 of them at F by 2. If you don't change anything and just run 2 of them at F by 2, it doesn't help you, because you have to take advantage of the lower frequency by lowering the voltage. If you don't lower the voltage, it doesn't help. You have to essentially operate it at the most efficient voltage, the least possible voltage at which you can run the chip at that F by 2. Otherwise, there is no point in going from here to here.
The frequency will be low, then my power
Frequency is low, power consumption is low, but there are 2 of them. Okay, so you cannot say that. So that is not the way to look at it for this particular case. See, at the end of the day, there is a certain throughput it is required, right? You want to guarantee a certain throughput. Okay, so you have designed this chip which has this, let me come back to the encryption engine. So many encryptions per second you need to do. Okay, so there is a certain throughput which is required. So I can either do it using a single engine running at that frequency, or I can have 2 of them running at half the frequency and so on. So while doing that, I'm maintaining that, making sure that the throughput is being kept. But now I'm comparing which is better from a power perspective. And really depends on the throughput value. If it's a very low throughput design, then going parallel is not a good idea. You want to stay with a single one, reduce the frequency, and you're meeting the throughput, and you're also operating at a lower voltage, and it is true, as you increase frequency, power will go up, as you reduce frequency, power will come down. But that is not what we are talking now here. We are saying, for a given throughput, where should you be sitting? Right? I want this. Should I use 1 core, 2 core, 3 core? Clearly at this point you want to use 1 core. Beyond this point you want to use 2 core and so on. So depending on the throughput, you have to decide whether to go parallel. Parallel could also be temporal parallelism. That means you are pipelining it. Pipelining it is also essentially kind of parallelism because A and B are running in parallel. And you can do both. You can do pipelining and parallelism. You can do both simultaneously. Okay, so this is one very important technique which you are already seeing in industry. That's why people talk of multi-core, because you push performance by having more things running in parallel. Okay, so that each one can run at a lower frequency, and corresponding voltage is also used, so that you are at the lowest power point for that particular core. See, because it's a throughput enhancing mechanism. Pipelining allows you to increase throughput. See, if you see between here and here, right, even though maybe this labeling is a little misnomer, here I have to wait for a delay of A and B before I can give the next thing. Here what I can do is, if so the delay of only either A or B, let us assume A and B have the same delay, then only the A plus B's delay should be equal to 1 by f. Here only delay of A should be equal to 1 by f. So you have more time. A can now run half as fast in this case compared to this case, which means I can use lower voltage. I can run things slower, so I can use lower voltage, but I have not lost throughput because I am doing things in parallel. While A is happening, B is also happening. Okay, but it's chained in this way that A does something, gives it to B. A and B are both doing work in parallel. So that is why we are able to throughput of C. No, throughput of C and throughput of A is the same. What is not clearly, what here it means is delay of A plus B is 1 by f. Here delay of A or delay of B is 1 by f, which means in A, to keep the same throughput, you have to use a higher voltage. So this is again how you can reduce the voltage. Similarly, out here I can use a lower voltage. In part B I can use lower voltage because I have twice the amount of time to finish my job. Each path here has twice the amount of time compared to here. So I can use lower voltage. Of course, you see two things here. One is you need to distribute the information to once every alternate cycle, it goes up, comes down, goes up, comes down. Similarly, you have to collect it out here. So there is an overhead of distributing and collecting when you go parallel, spatial parallelism. Temporal parallelism, the overhead is additional sequencing elements. See, there is an additional sequencing element. So there is an overhead involved, and that overhead adds to the cost of parallelism. Right? So which you have to, the gain should be higher than the cost. And as you push the throughput, this cost, the gains become quite significant, and so it becomes better to go parallel. Either spatial or temporal or both, spatio-temporal parallelism. So what are the overheads of parallelism again? Basically, it's the overhead is essentially the, if you go temporal parallelism, which is pipelining, overhead is inserting those pipe stages, which is essentially the sequencing elements. Those flops themselves, you have extra gates, you have extra loading on the clock network because it has to drive all those flops. So there is extra power and area because of that. Similarly, if you do spatial parallelism, where you have number of entities physically, you just replicate the core multiple times, then you need to have something which distributes the work, some distributor, and then something has to collect it. So there is that overhead which is there. And of course, you might not be able to parallelize. What if you cannot parallelize? Maybe certain things, maybe you don't have enough parallelism. Then the extra cores are just sitting idle. Right? So there is a certain inefficiency because of that. And finally, to come back and answer the question which was raised earlier, what prevents me, why not go 100, why not go 1000? The other important consideration is area. Because clearly there is an area hit out here. You are doubling the area, and as I said, area translates to money. So there is a certain optimum chip size which you want to use, and within that chip size you want to pack it with as many things as possible. Do you pack it with a single monolithic extremely complicated core, or do you have a number of simpler cores, or somewhere in between? Right? So that is where, that is kind of the architectural questions which you have to ask as a chip designer. And if you see, the trend is to go towards multiple cores. Maybe each one is a little simpler, so each is efficient, but then you have many of them running in parallel. And of course, there is this problem of how do you keep all of these cores busy so that you reduce the inefficiency of parallelization. When these cores are general purpose microprocessors, then the whole programming, everything, the whole infrastructure has to change to support efficient usage of these multiple cores. Whereas if it is something where it's a signal processing engine or data flow type thing, then as a designer it's kind of fairly straightforward for you to just keep on cycling and giving job to each one in a sequential fashion. Now we saw how we can reduce the frequency by going parallel, but even if I have, no matter whether I am parallel or serial or whatever, if I have a particular core, maybe I don't need to always run it at the max frequency. Maybe I can reduce the frequency. For example, now in this processor, in this laptop, it's not doing much work. So the frequency can come down quite a bit. Instead of running at 2 gigahertz, it can come down to maybe 500 megahertz. Okay, being able to dynamically adjust the frequency is called dynamic frequency scale, right? Because throughput demands vary dynamically, and so you adjust the frequency to what is required to meet the throughput. And you know that if you didn't do anything else, just reduce the frequency, power is proportional to frequency. It's not more energy efficient, but it is power efficient. That means my heating will go down, it will not become as hot, right? Because I am running at lower frequency and so lower power. And how do you adjust this frequency? Well, you have something called typically in any of these chips you will have a clock source, you'll have a reference clock coming in. There's something called a PLL, phase lock loop. The reference clock will be a few megahertz, a phase lock loop will multiply it and generate an internal clock which is running at whatever frequency you want, few gigahertz. And that multiplication factor you can change if you want. Okay, so that is one way, but PLLs are very, it turns out PLLs have time constants which are in the kilohertz, perhaps in the megahertz range. So it takes a while for a PLL. If you change the divider ratio, the multiplication factor, it takes a while for it to adjust. So for that time you have to just be waiting. It can take microseconds, milliseconds, depending on the PLL design. Instead, what you can do, a simple way of changing the clock frequency, is use dividers. You have, say, you generate a 4 gigahertz clock. Your chip requires 2 gigahertz maximum. You cannot go beyond 2 gigahertz. You have a 4 gigahertz clock coming, which you divide by 2 to get 2 gigahertz. If I want 1 gigahertz, I put another divide, so on. I don't do anything to the PLL. Everything is done digitally outside. So that is what these guys do. Here, simple idea, f comes in, f by 2, f by 4 till f by 2 to the k. So many divide factors are there. It's already being generated and the divider is, so many dividers are there. In fact, one divider and you just tap off from different points. And you get these, then you mux and select which one you want. So if I want any of these frequencies, just a simple setting of the mux to get me that frequency. Okay. But of course, if you recall what we need to do here, mux, control of the mux, you have to be careful. Okay, so think about how you would do the control of the mux so that you don't have false edges coming in. Okay, whatever you looked at for the clock gating, you can apply something similar out here. That is not being shown just for sake of detail, I guess. In addition, if I want, these are just divide by 2 ratios. If you want something in between, what do you do? Right? So what these guys propose is what is called clock thinning. They have a little state machine, and what is frequency at the end of the day? It is some number of edges per second. So if I want, instead of 32 megahertz, I want 31 megahertz, it is 31 million edges per second, right? Or per microsecond, it is 31 edges. So you just count and you suppress. That's what they do. So that way they can adjust the clock frequency.
This clock I'm using for some device, and there's some set and hold times for the device. If I divide the clock this way and set, then why we do
Okay, so the point here is that in this, of course, you have to make sure that the device, see, when it's running at f by 2, okay, your critical paths have to be able to run at f by 2. It should, all the timing should work at f by 2. Similarly, f by 4, f by etc. Okay. This is basically to, yeah, it is for reducing power. Exactly, it's for reducing power only. That's why you do this. Okay. So, but you have to make sure that it will run at f by 2. Now the thing is, we know that when I reduce my when I reduce my frequency, I'm kind of going back like this. If I'm going to use, instead of f by 2, f by 4, then the natural question is, why not reduce the supply voltage also? So not just reduce power, but I also reduce energy and make it even better, right? If you go back to the equation, power, when I also reduce frequency as a function of voltage, when I reduce frequency and also adjust voltage, my power reduction is much more. So that leads to what is called dynamic voltage and frequency scaling. You change the frequency. If you use a reduced frequency, you reduce the voltage. You reduce the voltage such that your chip will still run at that particular frequency. Okay, so for example here, when I go from f by 2 to f by 4, see, if this was my f by 2 period, my f by 4 period becomes twice large. So I have more time. I can slow down. I can reduce the supply voltage, so everything runs a little slower. So I'm more energy efficient. Okay, now similarly between any two boundaries, say f by 4 and f by, between f by 2 and f by 4, any other frequency are better in this scheme, what they have. You have to use the voltage of f by 2, because you can end up with clock edges which are running at a period of the f by 2 clock. So your voltage has to be, for all these frequencies between f by 2 and f by 4, where you do this clock edge suppression thing, it better run at a voltage at which the f by 2 thing will run, because you can have two edges come very quickly. So your voltage should be set to be able to run there. Once I hit f by 4, I can change the voltage to what it will run at f by 4. Then between f by 4 and f by 8, again I use the voltage for f by 4 and so on. So you can do this, what is called dynamic voltage scaling. Except you have this issue where you take when you design a chip, okay, this is the frequency versus the voltage, okay. But what is that frequency versus voltage? For a particular chip, you will get a particular curve. But when you manufacture the chip, no two chips are the same. There is going to be a spread. So you will have this upper limits, the limits. They will be the fastest chips, which will basically, for the same voltage, if this was a typical chip, it will have a higher frequency. A slower chip will have, for the same voltage, lower frequency. You have a spread. So there is this band of chips. Okay, now typically what is called, before people used to do what is called worst case design. That means if you had a frequency target, let us say this was the frequency target of say 1 gigahertz, and you wanted to make the chip and give it to your customer. Say use this chip, but you have to tell him what voltage to use. You will say use my chip and use a voltage of 1.1 volts, and I'll guarantee you that my chips will run at 1 gigahertz. And how do you come up with 1.1 volts? That is the voltage at which your slowest chip will run, at 1 gigahertz. But then what will happen is that you have a lot of chips which can run at the same voltage of 1 gigahertz, at the same speed of 1 gigahertz at a lower voltage. Just because what is different in these chips is the threshold voltage. The threshold voltage is a random variable. It has a spread. It has a mean and it has a spread. These chips, when you say slow chips, VTH is high. VDD minus VTH is low, so speed is low. Here VTH is low, so speed is high. So fast to slow, this is the variation. This is the problem. So instead of doing worst case design, if you can adapt, that means per chip you set a voltage which is suitable for that chip. Don't just say I'm going to use the voltage for the bus, of this family of chips. Don't determine the voltage based on the black sheep in the family. Okay, you try to adjust the voltage for each chip individually so that on an average you are better off. So that is called adaptive voltage scaling. So you scale the voltage for that chip. What you do is, you have a range of voltages possible, right? Different chips will have different voltages. So somehow you have to figure out what is the right voltage for that chip. Okay, how do you figure that out? We'll kind of look at that in the next class, but the overall system kind of looks like this, of dynamic voltage scaling, dynamic voltage frequency, or adaptive voltage scaling system. What you have is now no longer is the supply voltage to the chip fixed 1.2 volts or whatever. What you have is a voltage regulator which you can control. There will be a control system sitting on the side which adjusts the voltage based on the actual requirement of the throughput. Some throughput is there, it will go and say, okay, requirement is there, okay, this is the frequency at which you need to run, and so for that frequency I know this is the voltage you need to set up. So it will go and adjust the voltage, adjust the frequency, so that you reduce the voltage, and hence you reduce the, if there is a battery sitting outside, you are reducing the energy taken from the battery. Okay, so basically now you have these closed loop systems which keep continuously adjusting the voltage drawn from the battery. Now there are two ways of doing this. One is you have a table which says for these throughputs use these voltages. F by 2 I use this voltage, etc. Right? So that is commonly done. So what you have is, let us say you have a band of, you have a target frequency of this much. Then what you say is, this is my fast chip, this is my slow chip. I'm going to use this voltage. You just set it up. You have a table which is globally programmed. Once you program after manufacturing, you just say this is the voltage I need to run, if this is the frequency, and that voltage will ensure that even the slowest chip will run at that frequency. If I want to run at some other frequency, I program this voltage, and so on. I'll have a set of frequencies. You don't need too many, maybe 4 or 5 different frequencies. For that 4 or 5 different voltages, each voltage is set such that the worst case chip will still run properly at that frequency. So you just do it once. But you're greedy or you want more efficiency, then for that chip specifically, if that chip is a fast chip, maybe you can reduce the voltage even more. Adaptive voltage scaling. So how do you do that? So maybe you have a way by which you characterize, when you do a testing, each chip you characterize. How do you characterize? The simplest way which is used to characterize is a ring oscillator. You put a ring oscillator, you measure the frequency of the ring oscillator. If the frequency of the ring oscillator is large, high, then what you expect? You measure it, it's higher, you say it's a fast chip. Then you use a different voltage setting. You program it to a different voltage setting for that frequency. Similarly, lower frequency of oscillation, you use a different voltage setting. So again, during testing, you can put these different ring oscillators, you measure the frequency, from there you have an idea for what is the kind of chip it is, slow chip, fast chip, and so on, and then you come up with this table which relates frequency versus voltage. So for that frequency, you look up the table, you program the switching regulator to set up that voltage. Okay, so that is something which is done now commonly. Of course, you can also try to be smarter, where instead of programming it with the voltage, characterizing it based on the ring oscillator and having set these settings only for fixed frequencies, any arbitrary frequency, if you want to find the best voltage, then what do you do? How do you do that? That we'll have a look at it in the next lecture. Okay, so, and then there's of course this question which we had also alluded to in the earlier class. How do you figure out when to make these changes? When to change these different modes? One is under control of the software. Maybe the programmer says now I'm going into low power mode, or it's an automated system which is continuously observing, and then it says okay, nothing much is happening, so let me dial it down. So there are two possible ways of doing this, and maybe a combination of both could also be done.